Good morning, class. Today we are going to start off with learning about per unit analysis. In the previous lecture videos and lectures, we started off with single phase analysis, three phase analysis, transformers, and even transmission lines. We will be studying generators later on, but in today's class, we are going to introduce to you a method or a scheme which would make it very easy to calculate quantities of power system. At first, let's go through the learning outcomes of this video. We will first go through the motivations of why we need such a system, and then we look at the per unit system in general and understand what are base values in a per unit system. What are the motivations for using a per unit system? When we learned transformers in the previous classes, one thing we noticed about transformers was that transformers introduce various voltages in your system. For example, the generator would be at say 15 kV, while transmission could be at 150 kV, while distribution could be at different values of 30 kV, 300 volts and 150 volts. In terms of finding out the values of our power system, it's easy to reflect the load from one side of the transformer to the other side of the transformer. But we still need to know what the turns ratio of each transformer is to find out the voltages and current at the primary or the secondary side of the transformer. It's easy if we have only one transformer, but imagine if I'm having a power system with thousands and thousands of transformers. How many turns ratio would the operator of the power system remember? So it becomes very difficult to calculate the voltage and current of the system at various points in the power system. And it's even more difficult for your system operators to observe the current situations of the system. What do I mean by that? Let's say I measure a voltage of 30 kV in one section of my power system, while the same 30 kV is measured in another section of my power system. Now, how do I know if 30 kV is what the designated value should be? Is it a good value or is it a bad value? Just by looking at these values, it's not possible to tell if 30 kV is a good voltage in the transmission section or if it is a good voltage at your distribution section. So we need something to normalize all these different values and take care of the different voltage levels in our power system. For that, we introduce the per unit system. In per unit system, we normalize the voltage and current at each location. And because the voltage levels are introduced due to transformers being used in the power system, we'll follow the transformer ratings for normalization of these values of voltage and current. What this does is that it makes the per unit values of both voltage and current to be around 1 per unit. So I can say that if a value is close to 1 per unit, I have a system which is good, or the system is working normally. So in a way, it allows the system operators to overlook the abnormalities in the systems very easily. For example, in the previous case, when we had a 30 kV value in the transmission section, we are using the transformer rating of 150 kV as its base. This gives us a per unit value of about 0.2. For the same 30 kV in a different section of our power system, we will be using a base of 30 kV, which gives me a per unit value of 1. So just by looking at these values, I can say that, oh, the transmission section of my power system is suffering from huge voltage drop. Hence, I have only 0.2 per unit, but my next section, the distribution section, is operating at 1 per unit. And hence, it is the right value here and it is the wrong value here. How do we define the per unit quantity? The per unit quantity of voltage, current, power and impedance is found by dividing the actual quantity by a base value of quantity. Imagine a system similar to percentage, where the base quantity is always 100, while we represent everything in terms of a percentage. But in per unit, the base value of the quantity is a function of if it's a voltage, current, power or impedance. The per unit value is denoted by PU and it is unitless. So remember not to put any unit when you are representing them in per unit values. All the base values here are real numbers. So we would not have anything like 1 angle 30 as a base value for a quantity. The actual quantity could be 1 angle 30, but the base quantity would never be a complex number, as they are all real numbers, and these values are represented by the subscript B. So if I have a voltage base, I will write it as VB, a current base would be IB, a impedance base would be ZB, and a power base would be SB. And these base values are used only to normalize the quantity. They don't change the value of your power system in any way. Now let's first look at the base value for voltage. One of the reasons why we are introducing the per unit system is because of the different voltage levels in your system, which are introduced by transformers in your system. So what transformer does is that it separates your overall circuit or power system into different zones, each with a different voltage level. So we'll set the base value quantity for the voltage following the transformer's voltage ratio. There's a difference between following the transformer's voltage and the voltage ratio. Why? Because we want to maintain the relative voltage across the whole power system. We are going to use the transformer's voltage ratio. So we set the base value of quantity for the voltages in each zone following the transformer's voltage ratio. So for example, if I have the first value here, I take it as one base value. I'm going to use the transformer voltage ratio to find the base value for the next zone and the next zone and the next zone and the final zone in this example. Let's have a look at an example to find out how to find the base voltage for the different section. So let's consider the following electrical energy system. The first thing we have to find out is how many zones, that is with different voltage levels, does this system have. So we'll have first the generator section, which would be at 15 kV. Then we'll have the transmission section, which is at 150 kV. Then we have distribution section 1, which is at 30 kV. Then we have another distribution section zone 4, which is at 300 volts. And finally we have the voltage to your households or your houses or HDBs, which is at 150 volts. So in total I have 5 zones here. The second is, let's find the base value of the voltage at each zone. The important thing to note here is that in a per unit system, each zone will have a different base voltage. So we can assume the base voltage of any one zone to be one value, and then we find the respective values of the base voltages for each different section. So let's start with zone 3. Let's assume the base voltage of zone 3 VB3 is equal to 30 kilovolts. So the base voltage of zone 2 is going to be the base voltage of zone 3 into the turns ratio between zone 2 and zone 3, which is 150 kV by 30 kV, which gives me a base voltage here of 150 kV. Similarly, the base voltage of zone 1 is going to be VB2 times 15 by 150, which is going to give me 15 kV in this case. And for VB4 we have VB3 times 300 by 30 kV is going to give me 300 volts. And finally, for our fifth base voltage for zone 5, it's 150 by 300 into VB4 is going to give me 150 volts. Remember that each of the base voltage have the units, but per unit values wouldn't have units. Let's look at another example to clear this concept up. So consider a single phase transformer, which is the turns ratio is 480 by 120. What's given to us is that the base value of the voltage on the primary side to be 480. So VB1 is equal to 480 volts, and the secondary side base voltage is VB2, which is 120 volts. If the voltage at the primary is measured to be 432 volts, the voltage at secondary side is 108 volts. So we have V1 is equal to 432 volts, and similarly because of that we have V2 is equal to 108 volts. The primary side per unit value is going to be V1 per unit, which is equal to the primary side voltage divided by the primary side base, which gives me 432 divided by 480, which is 0.9 per unit. Similarly, for the secondary side per unit value, we'll use the secondary side voltage V2 divided by the respective secondary side base, which is 108 divided by 120, which is equal to 0.9 per unit. So now we notice that the voltage in the primary and the secondary in per unit is the same value. The transformer turns ratio is taken care of in the per unit system because the primary and the secondary voltages are now the same value. I can represent the whole transformer by eliminating the turns of the transformer and thus eliminating any different voltage levels in my power system. The next part is we are going to understand how to find the base value for your complex power. We'll first choose the voltage base values following the transformer voltage rating. Then we select a single base complex power in the system, and this base value of power is used to normalize the quantity. Thus, the base value for the real power, reactive power and the complex power is the same real number. We already know how to find the base values for the voltage and the power. We can derive the base value of current from the base value of voltage and power. So, IB corresponds to SB divided by VB, and similarly the impedance base value, again which is the same for impedance, resistance or reactance, can be calculated from voltage and current. So the impedance base value can be written as VB by IB, or by substituting the value of IB from the previous case, we can say it's VB by SB by VB, which gives me V base square by the S base. So I can say that the Z base corresponds to V base square by S base. Now these values of current and impedance can be used to find the I per unit values here for different values of current and your Z per unit values for your different impedances, resistances or reactances in your system. In summary, we learned what is the motivation behind a per unit system. Secondly, we understood what is meant by a per unit system and found out what are the base values for voltage, a VB or a voltage base for each zone of your power system. Power base have SB, you only have one power base in the whole power system. Then we have the current base, which is derived from your S base by V base, and finally we have our impedance base, which is again derived from your voltage divided by your base current, which can be simplified to give you V base square by S base. Thank you.